So, yeah, fine. Okay, so yeah, welcome back to another NPTEL class for chemical engineering, and today we'll be looking into a topic called mechanical operations. So previously, till the last class, we were trying to complete chemical reaction engineering CRE, both 1 and 2. So today will be the start of the mechanical operations, which is a different subject. And when it comes to mechanical operations, the subject is fairly straightforward. So most of the questions from mechanical operations are fairly direct in nature, and mostly it's easily solvable as well. And compared to CRE, mechanical operations is not that lengthy in terms of syllabus and portions. But anyways, let's get into the subject and let's see how it goes. So mechanical operations, you know, so by definition, mechanical operations is a branch of science and engineering dealing with the practice, description, and study of processing, handling, characterization, conversion, and use of a wide variety of particulate materials, both wet or dry, in sizes ranging from microns to centimeters, based on the general theory concerned with the physical properties of finely divided substances, including powders, crystalline solids, granules, dispersions, slurries, and pastes. So this is the very detailed definition of mechanical operations, and long story short, mechanical operation is a branch of engineering and science that deals with different particles basically. So this different particles can be of any type of different types, and it can be of different shapes and sizes as well. So basically, this is the more compact or brief definition of mechanical operations. It deals with not just deals with the handling of different particles of different types, shapes, and sizes. So this is the very basic definition of this term mechanical operations. So in mechanical operations, as we just mentioned, we deal with mainly particles. And these particles, it can be as the definition says, it can be anything. It can be something like a spherical solid, or it can be an undefined shape like this, or it could be very fine particles forming a slurry or a paste. So it could be anything. So usually we use two things to classify or characterize these particles. So one such characterization can be done by the shape of the particle, and the other characterization is by the size of the particle. Right. So let's look into how we can characterize a particle based on its shape. So when it comes to shape, there is one term that we need to learn when it comes to the shape of a particle, and that is called as sphericity. So sphericity, it is represented as phi, or in some terms it is also represented as phi s, or the s for the sphericity. So it is basically the ratio of surface to volume ratio of sphere by surface to volume ratio of the concerned particle, right? So basically what this sphericity tries to do is it tries to make the particle in equivalence with the sphere by taking the surface to volume ratio of the sphere and the surface to volume ratio of the particle, right? So you can have a general definition or the general equation for sphericity as well. So phi s surface to volume ratio of sphere will be what? Surface area of sphere, that is 4 pi r square or 4 pi dp square by 4 divided by volume, that is 4 by 3 pi dp by 2 the whole cube, the whole by for surface ratio to that of particle. Let's say Sp is the surface area of the particle by Vp. Let's say Vp is the volume of the particle. So here basically dP means the diameter, Sp is the surface area, and Vp is the volume of the, and the P represents the particle. So volume of the particle. So you can cancel out all these, constants and whatnot, and you can come at a very simple equation like this. So sphericity phi s will be 6 Vp by Sp dP. So this is the basic equation of sphericity of a particle. So this equation, it's very important for you to remember, because a lot of questions from mechanical operations are based on sphericity. So it is an important equation. So anyways, when I said dP, what this dP essentially means is that dP is the diameter of the sphere having the same volume as that of the particle. So basically what this means is the dP that we used here in both the numerator and denominator, it is the diameter of a sphere. Let's say this is the sphere. This sphere has the same volume as that of the irregular particle that we are trying to describe by using this sphericity, right? So this is 4 by 3 pi dp cube by dp by 2 and 2 cube, that is 8. So yeah, so this will be the volume of the sphere, and let's say this is the volume of the particle Vp, and Sp will be the surface area of this particle. So basically, by definition, we just applied all these things in the definition and we got this formula, simple formula here. Sphericity phi s is equal to 6 Vp by Sp dP. Now, of course, since we are trying to define sphericity with respect to a sphere, it should be pretty much given that sphericity of a sphere is basically 1. And this is the maximum, this is normally the maximum value that you can get for sphericity. So basically what this means is sphere is the most spherical particle that you can find. So yes, so sphericity of a sphere is 1, and any other shape that you take, whether it is cylindrical or let's say cube, anything, the sphericity will always be less than 1, right? And the sphericity of these particles, you can also find it using the same formula here, 6 Vp by Sp dp, where Vp means the volume of the cylinder, Sp means the surface area of the cylinder, and dp is the diameter that I just defined above. And you can do the same for a cube as well, right? So yes, so yeah, so that is about sphericity. Now another term with regards to the shape characterization of particles is something called as surface shape factor, and you can represent this as S. This is basically the reciprocal of the sphericity. So this will be SPdP by 6Vp. So this is just one extra term, with regards to the shape characterization, that is surface shape factor. So obviously, since sphericity of sphere is 1, that means the surface shape factor of the sphere is also 1. And also, since sphericity of other, shapes are less than 1, the surface shape factor will obviously be greater than. So that is the thing with regards to the characterization of particles with respect to the shape. Now the second characterization tool that we use is with regards to the particle size. So you can have a lot of definitions with regards to particle size. So if someone says coarse particles, that means the average size of the particle are somewhere between millimeter to centimeter range. And the perfect example you can say is gravel, or very very coarse sand. So you can say so coarse particles are the usually the typically the largest in size range, while we think about the particles that we handle using mechanical operations. And then comes fine particles. So these will be, by the name itself, these will be like, very less in size. And usually the size of these fine particles are defined with respect to mesh sizes. So you must have come across something called as a sieve. So on a sieve, holder, you have a lot of mesh sizes through which you can sieve out, different sizes of particles. So basically, these fine particles are defined in terms of their mesh sizes. So we'll come back to this mesh. So mesh, will usually the mesh that people use are in the Taylor series mesh. So we'll visit that at a later point in time. But anyways, that is about fine particles. And of course, we have something called as very fine particles, and these will be usually, in a range something like, let's say micrometers to millimeter range. And then you have ultra fine particles. So that will be typically in the range of 1 micrometer or lesser. So these are all some of the different size ranges that you can come across when people talk about a particle size. of a or a size of a particle, right? So yeah. So anyways, let's get into the characterization. So when we define particle size, we use various terms actually. So the but we try to define everything in terms of a sphere. So everything, if the particle size we'll try to define it in terms of a diameter. So we must have come across this term equivalent diameter. So you must have come across this equivalent diameter a lot of times. So this is one of the things that we use to characterize a size of the particle. And you have a lot of these kinds of equivalent diameters. So for example, one such diameter will be the arithmetic mean diameter. So this is basically the arithmetic mean of the diameters of particles. So let's say you have, one, two, three, four. So you have four particles like this. So let's say one of the particles has a diameter of one millimeter or whatever the unit be. Let's just keep it arbitrary. So one of the diameters is one. Then we have a diameter of two, three, and four. And let's say all of them are in equal sizes, then the arithmetic mean, what is the arithmetic mean here? Basically, it's just sum of these diameters, the whole divided by number of particles, 4, right? So this is what 3 plus 6 plus, so there is 10 by 4, or 2.5 is your arithmetic mean. So let's say you have these particles in different mass fractions. So let's say, this the mass fraction of this is x1, mass fraction of the second type of particle is x2, x3, x4, and so on. And let us just represent the diameter as d1, d2, d3, and d4, right? So then your arithmetic mean diameter, let us represent it as dn. So this will be, you know xi or x1 d1 plus x2 d2 plus x3 d3. Okay. Let's not complicate this like this. Okay. Yeah. So instead of mass fraction, what we'll do is we'll just take the pure number of these particles. Okay. So let us say we have a total of n particles. Okay. So we have a total of n particles. Let us say we have n1 number of particles of diameter 1, n2 number of particles of having diameter 2, then n3 and n4 number of particles for diameters having 3 and 4. And similarly, let us say, take the diameters as d1, d2, d3, and d4. And n will say, nt. Nt is the total number of particles that we have in the particle mixture. So that means, your arithmetic mean, let's say dn, will be n1 d1 by nt plus n2 d2 by nt plus n3 d3 by nt plus n4 d4 by nt. So basically, you are just taking the arithmetic mean of the diameters by taking the number of particles having that diameter into account, right? So if you write a general formula for this arithmetic mean diameter, you will get something like dn is equal to sigma I equal to 1 to n ni di by nt, where ni is the number of particles having a diameter di. So n1 will be the number of particles having the diameter d1, n2 will be the number of particles having a diameter d2, and so on. And nt, as defined earlier, is the total number of particles. So yes, so this is what you mean by arithmetic mean diameter. Now you can have something like, mass mean diameter. Like this is another type of equivalent diameter that you can get. Mass mean diameter. So this is basically, let's say dm will be sigma of I equal to 1 to n xi di, where xi is basically your mass fraction of particles having a diameter di. So this is another mean diameter that we can define you for characterizing the sizes of particles. Then you can have something like a volume mean diameter. So volume mean diameter is basically the mean diameter of a sphere having the same volume as that of the particle. So we were using something like this in our definition for sphericity. So this is that BP here, basically, which is the volume mean diameter. And that is the mean diameter of a sphere having the same volume as that of the particle. Now, the formula for mean volume mean diameter, you can write it as dV is equal to 1 by sigma of xi by dpi cube, the whole raised to 1 by 3. Yes. So xi here will be the mass fraction, dpi will be the diameter of the particle, and xi will be the mass fraction of particles having a diameter dpi. Right. So this is the thing about volume mean diameter. And then there is one more diameter, which is, surface sorry volume surface mean diameter. So by definition, this volume mean surface mean diameter is that diameter of a sphere having the same volume to surface ratio as that of the particle. So basically the volume to surface ratio, so volume of a sphere by surface area of the sphere will be equal to the volume of the particle by surface area of the particle. So the diameter of this sphere, let's say dvs, let's say. So the diameter of this sphere, which has the same volume to surface ratio as that of the particle, and that diameter is called as the volume surface mean diameter. And to represent this, we can write dvs is equal to 1 by sigma of xi by dpi. So this will be the volume surface mean diameter. Another name that this is known as is the Sauter mean diameter. Right? So yes, so these are just some of the terminologies that are usually used to describe or characterize a particle based on the size of the particle. So again, that is how a particle is characterized, either based on its shape. We'll be using something like a sphericity to characterize it based on its shape, or we'll be using something like these definitions that we just went through with the equivalent diameters to characterize it in terms of the size of the particle. So that is it for the characterization of particles. Now, one more topic we'll try to cover today is the basics of size reduction. So size reduction, that as the name suggests, we are just trying to reduce the size of the particles by trying to incorporate some unit operation or a mechanical operation. So yeah, so we are basically just trying to reduce the size of the particle. So you must have something like a mixie at your homes. Basically, mixie is a sort of a size reducing equipment. So you put something which is of a bigger size in the mixie, it will shred it, and you will get it in a much smaller, fine pieces. So size reduction is basically that, just trying to reduce the size of the particle. Now this size reduction happens via four different principles. The first one is compression. So compression, basically means, let's say you have a particle, and let's say you have a steel plate like this or a hard plate, and we are just trying to compress this particle like this by applying forces on the opposite direction towards the particle. And what happens is, because of this compression or this force that is applied on the particle, this will start to crack, and it will form various different products. This is the very simple layman terminology or definition of the compression principle of size reduction. So that is compression. Then you have something called as impact. So for impact, basically, let's say you have a particle like this, and you have another, particle. So these can be both same particles, or it can be different as well. So what happens here is, these particles will collide with each other, usually at very high velocities, and this collision will break either one of the particles or in some cases both the particles. So that kind of a size reduction is called as impact. Then you have something called as a attrition. Now in attrition, the same, let's take two particles. So these can be either the same two particles or these can be different as well. So what happens is, instead of directly colliding with each other, it will go and, let's say, something like a rub with each other. The forces will be somewhat tangential to the surface of these particles. And what happens is, when you have a surface like this and there is some tangential force that is coming like this, a small part of it will crack, and you will have a small particle that gets separated from the bulk of the particle. The same happens to both these. Most sometimes in some cases only one of these particles will undergo attrition, but in some cases both these particles can also go attrition. So these tangential forces, or you can even call them as shear forces. So these shear forces will act on these particles, and via this way, via using these shear forces, the attrition will happen. And then one more terminology is the cutting. So the mixie, as I said, is the perfect example for cutting. So usually you have a particle like this, you just cut it using a very sharp object like a knife or a blade or whatever. So that is basically cutting. So these are the four major, principles or pathways by which size reduction can happen in any of the, mechanical operations. So, you have a variety of size reducing equipments. You have a variety of size reducing equipments. Different equipments follow different principle of, breaking down your particles or reducing the size of your particles. So for example, you have something like a crusher, or the most common crusher is a jaw crusher. So this jaw crusher usually uses compression to break down your particle and reduce its size. So usually these jaw crushers can handle feeds up to 6 feet in diameter. So these feed, you can reduce it to something like in a scale of millimeter to centimeter scale. So like the average size, you can say something like 0.25. So 6 feet product, I mean feedstock, you can convert it into something like, let's say, 0.25 inch feed feedstock, I mean product. So jaw crusher. So you have a lot of different other crushers as well. You have something like a gyratory crusher, and so on. Then you have crushing rolls and so on. So this is one type of equipment which are the crushers. Then you have something called as grinders. And the major principle in grinders will be, impact and attrition. So some types of grinders will be, hammer mill, or you have something called as attrition mill. You must have heard this term a lot as well, ball mill. So each of these mills have different procedures or working principles by which they reduce the size of the particles, but these are just some of the particles or some of the size reducing equipments that come under the grinder classification. So, for example, in a ball mill, you can put something like a 10-inch, not a ball mill, sorry. Yeah. So in a, let's say in a hammer mill, you can put something like a 10-inch feedstock, and you can reduce it to something like less than 1 inch size, up to something like a 20 mesh size product. So that is the operating size capacity for a hammer mill. In ball mill, you can handle um, something like a 50, yeah, 50 feedstock. You can reduce it to something like 200 mesh size particles. So these are just some of the size ranges through which these mills operate, the different mills operate. So that is about it for the grinder classification. And then of course you have cutting machines, and these are the most common example that I gave is the mixie at your homes. So this will also follow the cutting principle, and a lot of these cutting machines will have different kinds of principles and size ranges that through which they can operate. So some other examples of cutting machine will be knife cutters, then dicers, and so on. Then the final type of size reducing equipment will be ultra fine grinders. So these kinds of ultra fine grinders will give you products in the range of 1 to 20 micrometers or microns. So this will be the output product range that you will be getting from ultra fine grinders. So one of some of the examples of ultra fine grinders will be fluid energized mill, and then agitated mill. So in these ultra fine grinders, you can put very small particles like in the range of dia feedstock. We can put inside these fluid ultra fine grinders, and you will get very fine particles in the range of 1 to 20 micrometers. And the principle of ultra fine grinders are also attrition. The main principle is attrition and also impact, right? So yes, so that's it about these size reducing equipments. So we'll stop with the theory for this class. So the next in the we'll be discussing much in detail with regards to some of these equipments. For example, this ball mill and roll crushers and so on. We'll discuss some of the principles in detail in the coming classes. But for the time being, we'll stop here with this. So any doubts so far? Please feel free to voice out, and if everything is clear, we can move on to solving some of the old question papers. Yeah, okay. Yeah. So shorter mean diameter is basically, you, let's say you have a sphere like this, and the volume to surface ratio of this sphere, you can write it as volume V sphere by a sphere. So, and you have a particle which has the same volume to surface ratio as that of this sphere. So such a diameter, you can represent it as the volume surface mean diameter, or by definition, the volume surface mean diameter is basically the diameter of a sphere having the same volume to surface ratio as that of the particle. So, you know, yeah, that is what is called as a volume surface mean diameter. And you can like use this, V by S of a sphere equal to V by S of the particle, and you can derive this equation for the volume surface mean diameter as dVs is equal to 1 by sigma of xi by dpi, where here xi is again the mass fraction and dpi is the diameter of the particle having the mass fraction xi. Okay, so this is also called as shorter mean diameter. Now, in the other hand, the arithmetic mean diameter is basically the arithmetic mean of the various diameters that the mixture of particles has. So, the example that I gave here is, let's say you have four different kinds of particles. So, that is represented as these four spheres. So you have, let's say, four different kinds of particles, and let's say N1, N2, N3, N4 be the number of these particles that is available in the mixture, and D1, D2, D3, D4 be the diameter of these particles available in the mixture. So then arithmetic mean diameter will be basically, Dn equal to N1 D1 by Nt plus N2 D2 by Nt plus N3 D3 by Nt plus N4 D4 by Nt. So Nt is basically, here is the total number of particles available in the mixture. So basically what you're doing here is, it's an arithmetic mean that you're taking for the different diameters that is available in the mixture. So that is what is known as an arithmetic mean diameter. Yeah, fine. So just take a couple of minutes. We'll try to solve some previous year questions, and yeah. Okay, fine. Let's try to solve this question. This is a question from GATE 2019, GATE Chemical Engineering, question number 7. Consider a cylinder diameter d and length d, a sphere of diameter d, and a cube of length d. Which of the following statements concerning the sphericity phi of the above objects is true? And the four options are given as below. So this is a question from sphericity part from mass transfer operations, and the reference NPTEL can be found in Unit 1, Lecture 3, Characterization of a Single Particle Mechanical Operations by Professor Shabina Khanum, Department of Chemical Engineering, IIT Roorkee. So here they have asked us to compare the sphericity of three different shapes, which are sphere, cylinder, and cube. Also, by definition, sphericity phi can be defined as the surface to volume ratio of a sphere by surface to volume ratio of the particle. And the general formula for sphericity can be represented as 6 Vp by Sp dP, where Vp is the volume of the particle, Sp is the surface area of the particle, and dP is the diameter of the particle. Now, since sphere has a sphericity as 1, and this is the maximum value for sphericity. Now, in all these 4 options, only option A has the option where sphere has the highest sphericity. In all the other options, the sphericity of the sphere is not the maximum value. So, in short, option A here is the right answer by this logic. And of course, we can verify the same by using this formula phi is equal to 6 Vp by Sp dP for sphere, cylinder and cube, and we can find that the sphericity of a sphere is equal to 1. Then the sphericity of the cylinder by using this formula 6 Vp by Sp dP. Now they have given that the diameter and length of the cylinder is d. So 6 into Vp volume of a cylinder, that is volume of the cylinder will be pi d square by 4 into h, and here h is also d, so this will be pi d cube by 4. So this will be pi d cube by 4 by Sp, that is the surface area of the cylinder, that will be pi d into h plus 2 pi d square by 4. So this will be the total surface area of a sphere, and here also h, the height h will be equal to d. So this surface area is also pi d square plus 2 pi d square by 4. And then you have the diameter of the particle dP as d. So you can substitute this Sp and dP here, and we'll get a value of the sphericity of the cylinder somewhere approximately 0.667. And if we do the same, and in a similar fashion, we can write the sphericity of cube as 6 Vp by Sp dP, and this will be even less than 0.667. So by this logic, option A is the right answer for this question. Right? So I didn't do the whole math here. What I want you guys to do is do the math and just verify this answer, whether this answer is right or not. I did give you some of the logic behind these calculations. So just do it by yourself, and let me know what is the exact value of the sphericity for the cylinder and cube. Okay. Yeah. Fine. Let's move on to the next question. So this is a question from GATE 2017 from Chemical Engineering. Question number 10. Which of the following is the correct sequence of equipment for size reduction of solids? And the four options are given as below. So this is a question from size reduction part in mechanical operations, and with reference NPTEL lecture can be found in Unit 3, Lecture 14 and 15, Size Reduction Equipment 1 and 2, Mechanical Operations by Professor Shabina Khanam, Department of Chemical Engineering, IIT Roorkee. So here we have three different kinds of equipments that are given in these options. So the first one is jaw crusher, then a hammer mill, and a fluid energy mill. So jaw crusher is a type of crusher which usually turns your feedstock into products ranging in the range of 0.25 inches product, or this is approximately 0.5 to 1 centimeter. On the other hand, hammer mill usually reduces your particle size in the range of millimeters to less than 0.5 centimeter. So this is the handling size range for a hammer mill. But on the other hand, fluid energy mill is a very ultra fine grinder. And the principle of fluid energy mill is based on attrition mainly and some part of impact. And this leads to fluid energy mill giving out particles which are ultra fine in nature, or that means which are particles having less than 10 micrometer diameter. So from this data, we can say that jaw crusher has the highest range of sizes for the product, that is followed by hammer mill, and this is then followed by fluid energy mill. So this order is followed only in the option D. So the right answer here is option D, jaw crusher followed by hammer mill followed by fluid energy mill. Right. So we looked into these size ranges a while ago as well. So usually, these ultra fine grinders will give you the least, I mean, the most size reduced particles or ultra fine particles basically. And their size range will be, in the order of 1 to 20 micrometers. So fluid energy mills should come at the last, and jaw crushers are usually the first line of crushers. So basically, if you want to crush something like a rock or a huge particle of having some 6 to 6 feet, particle size or something, jaw crusher is the first line of crushing, and then you can put it in a hammer mill to reduce it to millimeter range, and these millimeter particles you can put it in the fluid energy mill and reduce it to even ultra fine particles. So this is the order here for this question. Okay, so if there are no doubts, we'll stop here for now, or if you guys want, we can go through one more question. So we'll do that. We have one more question, so we can do that if you want. Okay. Fine. This is a question from GATE 2014 from Chemical Engineering, question number 17. In order to produce fine solid particles between 5 and 10 micrometers, the approximate size reducing equipment is, and the options given are A. Fluid energy mill, B. Hammer mill, C. Jaw crusher, and D. Smooth roll crusher. This is a question from size reduction part in mechanical operations, and the reference NPTEL lecture can be found in Unit 3, Lecture 14 and 15, Size Reduction Equipment 1 and 2, Mechanical Operations by Professor Shabina Khanam, Department of Chemical Engineering, IIT Roorkee. So here we have four different crushers, rollers and mills which are used for reduction of size of particles. So in these four, jaw crusher usually handles very large particles of the range of 1 to 6 feet feedstock, and this will give particles in the product having a range of 0.25 inches product. And similarly, the product coming out of hammer mill will be in the range of millimeter to some centimeter range. Usually, product range less than 1 centimeter. And smooth roll crusher also has a similar range as these crushers and hammer mills. So the only option remaining here is fluid energy mill. So the concept of fluid energy mill is that we can see the concept using this schematic. So this is a brief schematic of fluid energy mill. So the feed enters like this and it is injected into the mill by a venturi injector, and under the bottom part of this mill will be grates having some windows through which air or superheated steam will be passed at very high velocities. So the air or steam will be passed inside this mill at very high velocities. So this air or superheated steam is what makes the particles fluidized inside this fluidized energy mill. And because these air and superheated steam are passed at very high velocities, this will lead to very high turbulence. And because of this very high turbulence, the particles inside this fluid energy mill will vigorously come in contact with each other and will undergo various attrition and impact forces. And this will lead to very small particles, or also called as ultra fine particles, which are usually in the range of 5 to 20 micrometer. So fluid energy mill is what we can use to produce fine solid particles between 5 and 10 micrometer. So the correct answer here is option A, fluid energy mill. Okay, so yeah, so this diagram here is basically a very simple schematic of a fluid energy mill. So I hope the explanation for the working principle of a fluid energy mill is somewhat clear. But anyways, as I said, for the fluidization to occur, we usually use air or superheated steam at very high velocities, which will in turn lead to very high turbulence inside the fluid energy mill. And this high turbulence will lead to a lot of attrition and impact between the particles that we are introducing. And this will lead to production of very ultra fine particles, which are in the range of 5 to 10 micrometers. So the correct option here is basically fluid energy mill. Right? Any doubts so far? Is this explanation clear? Okay. Fine then. Let's stop here for now, and we'll resume the same size reduction next class. So there are certain laws by which size reduction happens. You must have heard something like Rittinger's law, Kick's law, Bond's law, and so on. So we'll look into these different laws of size reduction, and if possible, we'll also look into a bit about this various working principles of the different size reducing equipments like the roll crushers and ball mills and so on. Right. So that's it for today. And one doubt I have: any one of you guys know when is the GATE exam for chemical engineering? On which date the GATE exam will happen for chemical engineering? Okay, the date is not yet announced, right? Okay, okay, fine, fine. Fine then. That's it for today's class then. Thank you for joining, and I hope to see you guys during next Monday.